So now that we know how to find our maximum amount of product that we can create given a certain amount of reactants, we can now utilize that to determine a reaction yield. So we have 3 different yields to talk about. The theoretical yield of a chemical reaction is the amount of product that forms when all of the limiting reactant reacts to form the desired product. We talk about the theoretical yield as being the perfect world example. Everything in the reaction goes perfectly. I use up all of my limiting reactant. Nothing gets in the way. The temperature, the pressure, everything about those experimental pieces is perfect. And that's the maximum amount of my product that I can create. We then have the actual yield of the chemical reaction, which is the amount of product actually obtained from a reaction. So in a lab setting, we are not in a perfect world. We have things that are going to affect our chemical reactions from happening. Maybe we didn't measure out our reactants perfectly. Maybe there is a slight contamination. Maybe when we were heating this reaction up to react it further, we didn't get to the desired temperature. There are many things in the real world that can affect a chemical reaction. And this is what plagues chemists all day, every day, is figuring out how good of a yield they can get from their chemical reaction. So this is the real world example. So our actual yield and our theoretical yield are very rarely the same because it's very hard to get to perfectly the theoretical yield amount of our product. So the comparison of the actual yield and the theoretical yield is called the percent yield. And that tells us what percentage the actual yield is of the theoretical yield. The higher the percentage is, the percent yield is, the closer our actual yield is to our theoretical yield. Think of it like a test. Okay, we want to get 100 points. Our actual yield is however many points we actually get. Okay, the closer we are to that theoretical yield value, to in this case 100 points, the better our yield is going to be and the better the reaction was. Okay, so a high yield, a high percent is good. A low yield, a low percent is bad. Okay, so let's look at a few examples of this. What is the percent yield of a reaction that produces 12.5 grams of the gas CF2Cl2 when 32.9 grams of CCl4 reacts with excess HF? Now there are a lot of words and a lot of numbers in that problem, and we have to decipher what each of them are. So we want to know the percent yield, that's what we're looking for. And we know that this reaction produces 12.5 grams of CF2Cl2, which is one of our products. So because we know how much this reaction yields, this is the actual yield. That's how much we know we can get out from this reaction in the real world. That's our real world example. So we want to know what the percent yield is if I start off this reaction with 32.9 grams of carbon tetrachloride, CCl4. Now I tell you that this is excess HF, so the excess doesn't matter because we know our limiting reactant is what's controlling the amount of product we can make. So the HF doesn't matter. We don't care about it. It's there, there's enough of it to react fully, so it doesn't matter. The only thing that's going to affect the amount of product is going to be the carbon tetrachloride, CCl4. So the first thing we want to do is determine the theoretical yield. So we want to take this mass of CCl4 and convert it to a mass of our product. Okay, because we know that that's the maximum amount of product we can make from the limiting reactant. Once we find that theoretical yield, we're going to compare it to our actual yield using our equation, actual over theoretical multiplied by 100. So our first step is to determine the theoretical yield. So we start off with our mass of CCl4, 32.9 grams of CCl4. And we're going to convert it to moles. Why are we converting it to moles? Because I need to change it from one chemical species to another. I need to convert from a reactant to a product. And the only way to do that is through a mole-to-mole ratio. So I need to convert my mass of my reactant to moles so that I can use the mole-to-mole ratio to go from reactant to product. Okay, so we need to know our molar mass of carbon tetrachloride. So we get 12.01 plus 35.45 times 4. We get 153.81. So we get 153.81 grams is 1 mole. So we take that, we do 32.9 and divide it by that value. Okay, so we have 0.2139 moles of CCl4. Okay, so we're going to start there now, 0.2139, I can probably zoom in a little bit here, moles of CCl4. And we want to convert that to our moles of our product, which is going to be CF2Cl2, because that's the mass of the product that we have. Okay, so we're going to go to that product. We see it's in a 1-to-1 ratio. So we have 1 mole of CF2Cl2 and 1 mole of CCl4. So we get out 0.2139 moles of CF2Cl2. Now I can't compare that mole value to this mass value to find my yield because they're not in the same unit. So our percent yield has to be the same units. So the only way to do that is to convert this moles to grams. So we're going to take that 0.2139 moles of CF2Cl2 and convert that to mass. So 1 mole of CF2Cl2 has a molar mass of 120.91 grams. Okay, so we take that value of moles, we multiply it by 120.91, and we get 25.9 grams of CF2Cl2. Okay, so this right here, that 25.9, that's our theoretical yield. So we now have our actual yield up here and our theoretical yield. We have those values and they're in the same units. So now we just have to plug them in to our percent yield equation where we take the actual and divide it by the theoretical and multiply by 100. We just have to do that division to find our yield. So we take the 12.5 grams, that's our actual yield, and we divide it by the 25.9 grams and multiply by 100. So we take 12.5, divide it by 25.9, we multiply that by 100. And we get a percent yield of 48.3%. 3 sig figs because of our original problem having 3 sig figs. So that is our percent yield, 48.3%. So I only produced about half the amount of product I would expect to from this reaction. Okay, let's do another one. So a similar problem where I give you grams of a reactant and a product. We want to find the percent yield. The only thing is we don't have a balanced reaction yet. So the first thing that we're going to want to do is write out our balanced reaction. And we can't do that quite yet because this problem is missing one thing. So I got out copper metal and zinc sulfate. So the product of my reaction between copper 2 sulfate and excess zinc was copper metal and zinc 2 sulfate. So you can use that to write out your balanced chemical reaction. So do that now. Our balanced chemical reaction is balanced as we write it. Everything's in a 1-to-1 ratio, so we get copper sulfate. Copper 2 sulfate is CuSO4. They have equal but opposite charges. Plus zinc metal, which if it's in its metal state, then it has a charge of 0, so it's by itself. Then we get copper metal out plus zinc 2 sulfate, which is ZnSO4. So that's everything's in a 1-to-1 ratio. The next thing we want to do is complete this problem similar to how we did the last problem. We want to determine the theoretical yield from our mass of reactant and then compare that to the actual yield, which is given here as 0.392 grams of copper. So this is our theoretical yield because it's the product that we're getting out. So we know that copper 2 sulfate is our limiting reactant because the product says that we have excess zinc. So the only thing that's controlling the amount of product that we're getting out is the copper 2 sulfate. So we're going to start this problem off by taking the mass of copper 2 sulfate, that 1.274 grams, and we're going to convert that to moles. So in 1 mole of CuSO4, that has a molar mass of 159.61 grams. So we get out for that 1.274 divided by 159.61, and we get moles of 0.0079819 moles of CuSO4. We now want to convert that to moles of our product, which is copper. So for every 1 mole of copper sulfate, we get out 1 mole of copper solid. So this leaves us with 0.0079819 moles of copper. Now our actual yield is in units of grams, so I would need to convert my moles of copper to grams of copper so that they are in the same unit. You technically could also convert this grams of copper to moles of copper and then compare those. As long as they are in the same units, they're going to give you the same yield. So we know our molar mass of copper from our periodic table. It's right there as 63.55 grams. It's from the periodic table. So we take that 0.007 and we multiply it by 63.55 and we get out 0.507 grams of copper. Okay, so that's our theoretical yield. So if all of my copper sulfate reacts perfectly, I should get out 0.507 grams of copper. But we know from this reaction that we only get out 0.392 grams of copper, so we can find the percent yield by taking that actual amount, that 0.392, and dividing it by the theoretical 0.507 and multiplying it by 100. So we take 0.392, divide that by 0.507, and then we multiply that by 100. So we get a percent yield of 77.3%. And that's how much we yielded from this reaction. So we didn't get a perfect reaction because we are not in a perfect world, but we got a good amount of our product out from this reaction. A good rule of thumb to make sure you're on the right track, we would rarely have a percent yield that's going to be higher than 100. So percent yield should be lower than 100%. Okay, so that's always a good one, which means that our actual value is always going to be lower in amount than our theoretical. The number from the actual compared to the theoretical, actual will always be lower than the theoretical value in order to get a percentage of less than 100%. Now, in the actual real world, in a real chemistry lab, for amateur chemists in general chemistry labs, sometimes we get percent yields that are higher than 100, and that just comes down to contamination issues. Maybe our product wasn't dry or anything like that. So it is possible to have a percent yield that is higher than 100%, but in these kind of generated problems from our textbook, we would rarely see a percent yield that is higher than 100%, unless it clearly says there was a contamination in the student's lab. What is the percent yield from this contamination? And that would be higher than 100%. So most of the time you're going to see a percent that's lower than 100. If you have a percent that's higher than 100 or something that's really, really small, then you did something wrong and you're going to want to double check your work. Okay. What I want you to do now is try this problem completely on your own. So we have a very similar setup to our previous problems. I give you the balanced equation. I give you the masses of what we're starting with and what our yield is. So we have our starting product of calcium fluoride and our actual yield of HF. We want to find the percent yield of HF. So follow the same steps that we've done in our previous problems in order to find the percent yield for this specific problem. The first thing we're going to want to do is convert our 6 kilograms of calcium fluoride to grams. So 6 kilograms converts to grams by multiplying by 1,000, because there are a lot of grams in 1 kilogram. So we get this to be 6,000 grams of calcium fluoride. Once we have grams, we can use the molar mass to convert to moles. So in 1 mole of calcium fluoride, we have 78.08 grams. And we get out from this 6,000 divided by 78.08. So we get 76.844 moles of calcium fluoride. Okay, so now we have to take that moles of calcium fluoride and convert it to HF. So we're going to take 76.844 moles of CaF2, and we are going to convert it to HF. So for every 1 mole of calcium fluoride, we get out 2 moles of HF. So we take that 76 and we multiply it by 2. And we get out 153.688 moles of HF. our actual yield is in kilograms of HF, so we're going to want to convert this mole value of HF to kilograms. And the first step to do that is to take that 153.688 and use the molar mass to convert. That is 20.01 grams. And we get 3,075.307 grams of HF. And to convert it back to kilograms, we just divide by 1,000. So we get kilograms to be 3.0753 kilograms. We can round that off to 3.08 kilograms for sig figs. And then that's our theoretical yield. Here's our actual yield. We'll just take those two values and compare them. So we take the 2.86 kilograms of HF and divide it by the theoretical 3.08 kilograms and multiply by 100. We get a yield of 92.9%. There we go. Okay, on to another one. Here's another one that you should try on your own first before we go into it. A very similar setup to our previous examples. We're starting with kilograms again, so we're going to have to convert to grams and then to moles. So keep that in mind. So try this problem on your own and come back to check your work. So we're given our balanced reaction here. So the only thing that we have to do is convert from kilograms to grams of our reactant, and then from grams to moles, so that we can go between moles of our reactant to moles of product, so that we can compare to our actual yield. So we're going to start out with 8.0 times 10 to the 3 kilograms of this ilmenite, FeTiO3, and we're going to multiply by 1,000 to go from kilograms to grams. So that gives us 8.0 times 10 to the 6 grams. We can then use the molar mass of ilmenite in order to find the moles. So in 1 mole, it has a molar mass of 151.71 grams. So we take 8.0 times 10 to the 6, we divide it by 151.71, and we get a mole value of 52,732.186 moles of FeTiO3. We now want to convert from our reactant to our product, and that's all in a 1-to-1 mole ratio. I think everything in this reaction is a 1-to-1 mole ratio. So our product out of TiO2, titanium oxide, is also 52,732.186 moles. Okay, so our actual yield is in units of kilograms, so we're going to take that 52,732 and we are going to convert it from moles to grams using the molar mass. So 1 mole of TiO2, that's a 2, is 79.90 grams. So we'll multiply that by 79.9 and get out 42,133.01.69. That's grams. And to convert it to kilograms, we're going to divide by 1,000. So we get our mass out to be, we'll put it into scientific notation, 4.213 times 10 to the third kilograms. And that is going to be our theoretical yield. So our percent yield then is our actual, which is that 3.67 times 10 to the 3 kilograms divided by this 4.213 times 10 to the third kilograms multiplied by 100. So we'll take 3.67 times 10 to the 3 and divide it by our answer there and multiply by 100. And we get a yield of 87.1%. So that's our yield for that reaction, another good reaction, nice and high yield. Okay, let's keep practicing. Let's do another one. This was a problem we already did. I don't know how it got on there twice. I don't believe it's on your lecture packet twice, but if it is, just cross it out. We already did it. Feel free to re-practice it if you want. Okay, so we'll move on to our next one. Ethylene, an important industrial organic chemical, can be prepared by heating hexane at 100 degrees Celsius. If the yield of ethylene production is 42.5%, what mass of hexane must be used to produce 481 grams of ethylene? So this problem's a little bit different than what we've been doing. It requires us to work backwards. We're given the yield and we want to know the mass of our reactant that we need to get that yield. So the numbers were given. This is our percent yield. And that 481 grams is our actual yield. So they know that this reaction is not efficient and it only produces 42% of what it should. So if the desired amount is 481 grams, well, I need to know what that original mass is to get that type of yield. So my actual amount that I want to get is that 481 grams. So we can use that to find our theoretical yield, which we can then use to convert back to our reactant. So if we look at our percent yield equation, we know our percent yield is 42.5%. We know our actual is 481 grams. We don't know our theoretical, and we know we have to multiply this by 100. So we want to solve for our theoretical yield, because if we know the theoretical yield of product, we can convert it back to our limiting reactant. So we'll take this, we'll divide both sides by 100, get 0.425. We'll do a little algebra and say that our theoretical yield is equal to 481 grams divided by 0.425. That's our yield. So we take 481 and divide it by 0.425. So our theoretical yield here is 1,131 grams, 0.76 grams. And that's of ethylene, which is C2H4, which is our product. So now that we know the mass of ethylene, the theoretical mass of ethylene that we need, we can use that to convert back to our reactant of hexane. So we'll take that one, here I'll change colors. We'll take that 1,131 and we will convert that to moles. So 1 mole of ethylene has a molar mass of 28.06 grams. So we divide that by 28.06 and we get 40.33 moles. So 40.33 moles of C2H4 converts with a 1-to-1 ratio to hexane, which is our reactant. So we're converting from here to here. That's all in a 1-to-1 mole ratio. So that's 40.33 moles of hexane, which is C6H14. Now that we know the moles of our limiting reactant, we can convert that to mass of limiting reactant, which is what the problem is asking for, the mass of hexane. Okay, so we can convert that using its molar mass. So we take the 40.33 moles of hexane, C6H14, and we're going to multiply it by its molar mass of 86.02 grams. We'll take that value, we'll multiply it by 86.02, and we get a value of 3,469.508 grams. Now our problem has 3 significant figures, so our final answer should be 3.47 times 10 to the 3 grams of hexane, C6H14, to account for sig figs appropriately. Okay, so that's a similar type of problem that we've been doing, just working backwards now. So we can use our known yields of specific reactions to find how much of our reactant we need in order to produce a certain amount of product. Okay, I want to put everything from this lesson together now with this problem here. So, potassium chloride is used as a substitute for sodium chloride for individuals with high blood pressure. Potassium chloride is made from a reaction between chloride gas and potassium, given in the balanced equation 2K plus Cl2 goes to 2KCl. The first thing we want to do is identify the limiting reactant and the mass of KCl produced when 10 grams of chlorine gas reacts with 14 grams of potassium. The second thing we want to do is determine what is the mass of the excess reactant remaining when those two reactants react together. Finally, if the actual final mass of KCl is 13.5 grams, determine the percent yield for this problem. So take a second and pause your video and think about how you would go about each one of these steps, and feel free to try to solve each of them on your own, and then come back and review the video as your answer key. This problem is a long one, okay, but it is one that brings together everything that we've talked about in this entire chapter. So, the first part is asking us to identify the limiting reactant and the mass of KCl produced. So, we're going to do like we did in the beginning of our lesson, and we are going to find our limiting reactant given our masses of our reactants. So, we start with chlorine gas. We have 10 grams of chlorine gas, and we want to convert that to KCl. You can either go to moles of KCl or mass of KCl. It doesn't matter. They're each going to tell you which one is your limiting. I personally feel like going to mass of KCl for each of my reactants. That way it answers the second question of this problem altogether. So that's just what I'm going to do. If you want to stop at moles and determine your limiting reactant from there, and then only do the conversion from moles of KCl to grams of KCl after you've determined that, go for it. It does the same thing. So we have 10 grams of Cl2, and we are going to convert that to moles of Cl2 using the molar mass, 70.9 grams. Once we have moles of Cl2, which we can calculate, I'm going to try to keep it small to use up my space properly. So we have 10 divided by 70.9. We get out 0.14104. That's moles of Cl2. We can now convert this to moles of KCl using our balanced equation. So for every 1 mole of Cl2, we create 2 moles of KCl. So we take that 0.14 and we multiply it by 2 to get out 0.28208. And that's moles of KCl, which I'm going to convert to grams. 1 mole of KCl is 74.54 grams. So we get out 21, here I'll put it in a different color, we'll do pink. 21.0268 grams of KCl. Now if you wanted to stop here for this part and then for the next part also stop at moles and then compare, you can. It's going to tell you the same thing. So we can then start with our second product, which is, or second reactant I should say, which is 14 grams of potassium. We'll do the same steps. 1 mole of potassium has a mass of 39.09 grams. We get that from the periodic table directly. So we get 14 divided by 39.09. We get 0.35814 moles of potassium. We then use our mole to mole ratios to convert from reactant to product. So for every 2 moles of potassium used, we get out 2 moles of KCl used. So we just get out 0.35814 moles of KCl. So again, if you didn't want to convert to grams just yet, you could see that this is a higher mole value than this. So that K is not going to be our limiting reactant, Cl2 is, but we can just finish out the problem. We know that 1 mole of KCl has a mass of 74.54 grams. So we multiply 4.54, and we get 26.6963 grams of KCl. So we can see from either the mole values or the mass values that Cl2 is limiting because it produced the lesser amount of product. It limited the amount of product that we can make, therefore it is the limiting reactant. Okay, so that's A. We found the mass of KCl produced as well as the limiting reactant. All right here is our answer to that problem. Okay, here we'll erase some of these numbers for sig fig purposes. There we go. Okay. Our next question is asking us, what is the mass of excess reactant remaining when these two reactants come together? So we know that the maximum amount of KCl that we can form is 21.02 grams. We now want to determine how much excess reactant, how much K is left over. So for this problem, this is one that we can do 2 different ways. We can take our maximum amount of product, which is 21.02 grams of KCl, and we can convert that back to our excess reactant. So we just convert this to moles using the molar mass, 74.54. That's grams in 1 mole. We get 21.02 divided by 74.54. That's 0.28208 moles of KCl. We then convert that to moles of our excess reactant, which was the K, which is a 2-to-2 ratio, so 2 moles of KCl is 2 moles of K. So we get out 0.28208 moles of K that we need to use in this reaction. So finally we have to convert that moles of K to grams of K because we're only given the mass of potassium in this problem. So if I want to compare the mass of potassium, I'd have to convert that moles to grams. So we're going to take that 0.28208 moles of K and just convert that back to grams. So 1 mole of K is 39.09 grams. So oh, I have a typo. I did not copy from my calculator correctly. It's a small change, but you want to make sure that we are getting all these numbers perfect. And this is just coming down to rounding differences, sig fig changes, and everything like that. Okay, there we go. Now we can multiply by 39.09 times, there we go, forgot that part, 28199, and we get 11.0229 grams of K. Now this is the amount of K that was used up. Okay, that's how much I needed to produce 21.02 grams of KCl. Okay, I have some K left over. So what we want to do is take our initial mass of potassium, which was 14. I started with 14 grams. I only used up 11 grams, 11.02. We'll round it off for sig fig purposes. So the amount that's left over is the difference between those values. So we have 14.0 minus 11.02. So we have 2.98 grams of potassium left over. Okay, the next question now is asking us if the final mass of KCl is 13.5 grams, determine the percent yield. So the final mass of KCl that was produced is 13.5 grams. That makes this the actual yield. Our theoretical yield is the maximum amount of KCl that can be produced from our limiting reactant, which we already have from part A. So part A calculated our theoretical yield for us, meaning that the last part of this problem, C, all we have to do is take our actual yield, which is 13.5, divide it by the theoretical yield that we've already calculated in part A, and multiply that by 100. And we get out 64.2%. And that is our percent yield. So this problem nicely brings together all of what we've done in this chapter. We have a balanced equation using multimole ratios, using those multimole ratios to determine our limiting reactant and our theoretical yield of product, and then using that theoretical yield and comparing it to an actual yield of that product to get a percent yield of the reaction overall.